with you. Of course, I would love to have been at CERN right now because it's such an inspirational place. I want to start with this little newspaper clipping. It's actually from 1941 in the New York Times Magazine. It's about the Institute for Advanced Study, and I love the title, Seeking Eternal Truth in a World of Chaos. I also like the looming shadow of Einstein on the blackboard. And it just shows that, whatever the things that we all are involved in are, in these very difficult times where we can't see each other as much as we want to. Yes. Yeah. Okay. Good. Yeah. So that we have been here before as physicists, and so we should take the long view, and that's exactly what I want to do with you. And Wolfgang asked me to speak on, basically triggered by a column I wrote for the online magazine Quanta, which had the kind of provocative title, Contemplating the End of Physics. And I must say, I have to make a disclaimer. This is a personal view. I'm a very optimistic person, by the way. I'm trying to make a deeper philosophical point, and very much from a theoretical perspective. My hope is to provoke further discussion. Now, there are quite often, books or articles that claim the end of physics or even the end of science, like this famous book by John Hargan in 1996, Facing the Limits of Knowledge in the Twilight of the Scientific Age. Well, clearly, if we approach a millennium, there's a certain doom approaching. But I thought these were kind of famous last words, like the famous last words of this Civil War general, son Sedgwick. They couldn't hit an elephant at this distance. And that was literally the last thing he said. And I think actually, in some sense, and that's the point I'm going to make, the immediate past was great. I think we have a terrific present in terms of challenges, and the future will even much better. So let's go to the immediate past first. If you just see what happened in the last, say, 10 years in science, and particularly in physics, you can ask, were there any, what I would like to call 5-star breakthrough in science, which are, things that, somehow percolate across the world, that every newspaper has this on the front page, above the fold. And I would say there were 3 times in the last decade when this happened. Obviously, the first one, all very well known to you, was Higgs Dependent Day, July 4th, 2012. Clearly an incredible success. But then we were, in some sense, spoiled, because in February 2016 was the announcement of gravitational waves, which I made a similar splash. Of course, the actual discovery of the event was in September 15th, 2015. And then there was a third one just 2 years ago, in April 10th, when the black hole image from the Event Horizon Telescope was published. Actually, I was at the press conference. There were multiple press conferences. I was at the one in Brussels. And I remember that the commissioner, the EU commissioner, said that there was a spontaneous applause, a standing ovation. And he said he never ever saw a standing ovation at that particular location, where typically politicians make their speeches. Now, you might say, well, there is something in common with these 3 examples. First of all, they are all truly worldwide collaborations, literally, sometimes literally indeed, global laboratories using the planet Earth as our instrument. They are great operational complexity. They push the limits of technology in a dramatic way and achieving fantastic sensitivities. I will not say anything about the LHC, but it's remarkable that some of the most precise measurements in particle physics are often put into context as saying, well, it's measuring the distance to the moon to the size of a human hair. Actually, LIGO measured the distance, a 10 to the minus 23 strain, the distance to the nearest star up to a width of a human hair. The Event Horizon Telescope had a 10 microarc second resolution, that's actually seeing a tennis ball on the moon, or the atoms in your finger, if you would actually look at it, and a factor 1,000 more powerful magnification than any other instrument. But also they had very long timelines, often of many decades, of course, from theory to observation. If you look at this famous plot of the discovery of elementary particles, then the Higgs boson has set a record with 48 years from the original papers in 1964 to the announcement. But you could say that the graviton or gravitational waves and the black hole have even longer timelines of more than 100 years. So in some sense, these are successes of the past. In fact, Einstein's theory of general relativity, as it was announced on November 7th, 1919, by the way, it was not on the front page of the London Times. It was somewhere in an editorial. It was actually quite a modest news item, the overthrow of Newton. But then, of course, it was rapidly picked up, particularly by the US press. And so I think it sets somehow the stage of this kind of worldwide reactions. So I think that's, we should actually celebrate that fundamental physics, astrophysics, is able to literally capture the mind of the world. Now, let's move to the present. There is this famous quote from the US then Secretary of Defense, Donald Rumsfeld, when he was asked about, the failure of the invasion of Iraq, and he explained this philosophical point of the known knowns, the known unknowns, and the unknown unknowns. And I think that's a terrific question. What do we know in physics that we don't know? And often say, we're extremely fortunate because our cosmology friends tell us that roughly 95% of the physical universe measured in energy is unknown. And I think, other fields probably, have much smaller percentages of known structure. And there are many other challenges, not only dark matter and dark energy. I have to remind you that there are very many deep mysteries even built and buried in the standard model. There are many why questions. Why do we have these gauge groups, these forces, these representations, charges, masses? There's the issue of neutrino masses that actually points that there is something beyond the standard model in terms of perhaps a grand unified theory. There are serious doubts about our understanding of the matter-antimatter asymmetry in the universe. There's this very powerful hierarchy problem that the Higgs boson has not yet solved for us. And as I said, there is this kind of question of, is there any room of the unification of forces? So I think the image I have, and perhaps many of you, is that we are a little bit like these old map makers. They tried to chart the map of the world. They knew that there was a certain part that was well known to them. And then there was the part that was unknown. And often these map makers would write Hic sunt draconis. There are monsters here, dragons, sea monsters. So I have this image that, the known physics, that's perhaps the 5% that we understand with many, many questions. It's this little part of the map. And then we're exploring the rest of the map. And our sea monsters, are just beautiful names that we give to the unknowns. Whether it's dark matter, dark energy, supersymmetry, we have no idea what's out there. And perhaps all of us are in one of these little tiny ships in this vast ocean of the unknown. Now, I should also remind you that, some of these known unknowns were unknown unknowns not that long ago. And we should always remind us about, that science is the belief in the ignorance of experts, as Richard Feynman famously said. It's a body of statements. It's varying degrees of certainty. Some are most unsure, some nearly sure, but none are absolutely certain. And particularly as a theorist, I like to quote Francis Crick of the famous Crick and Watson discovery of the structure of DNA, who said, any theory that can account for all the facts is wrong, because some of the facts are always wrong. And I just want to, for your amusement, share one kind of famous anecdote. Perhaps some of you have seen this before. This something happened a few years ago in England, where somebody was baking an omelet and cracked an egg and discovered it had 2 yolks. And then he cracked another egg and it has again 2 yolks. And he cracked another one. In the end, he had 6 eggs. Each had double yolk, and the probability of finding a double yolk in an egg is roughly 1 in 1,000. So this seemed to be tremendous, like a truly magical number, a 1 in a quintillion chance. And then there was a long discussion where many chicken and egg experts that actually had their points of view. Well, perhaps there was like bioengineering, perhaps the eggs were picked in terms of their weight, perhaps it was a batch for a particular chicken. And there was a huge debate. And then one of these experts very truthfully said that one night he was walking through the supermarket, and certainly he saw boxes labeled double yolk eggs. And so that was the explanation of this effect. So we should always be conscious of that. So clearly tremendous challenges in the present. But I actually want to take a point further into the future. Now, there is a question that, again, Feynman, I think, asked, and you can all ask yourself, suppose that all knowledge would disappear today, and you have the possibility to send one message of limited length, say one tweet, to the future. What would you send? How would you compress all of scientific information? And Feynman's point of view was that he believed that the atomic hypothesis, that all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into another, that one sentence, in some sense, is the essence of all of modern science. Because if you're told that there are building blocks, you will start looking for them, and this will be, in some sense, perhaps the heart of what science is. So I would argue in this colloquium that this is perhaps the most important fact also for what the future of our field will be. So I would argue that the 20th century was a century of discovering building blocks, but that the 21st century will be much more about what we will make out of these building blocks. And we have to do this in a very grand view. So let me explain this with these two toys, two little cars, one made out of metal and one made out of Lego blocks. So what will happen if you go after a few weeks? What will happen to the two toys? Well, of course, the first one will remain the same, but the second will probably be built into something else. So the essence of discovering building blocks is that you can start building. So my point of view is that if you think about science as mapping nature, where there is this large part that is, but that what we haven't understood or we haven't discovered or we haven't seen, that's a very limited view of what science is or what physics is. And we should be much more expansive, also vis-a-vis nature, because we shouldn't only think about what is, but we should think about what could be. And the things that we can create in our laboratories are just nature progressing, but in an expanded, accelerated and fashion. So we are exploring this much larger space. And I think actually we are right at the edge where this is happening. And this is, I think, extremely exciting because now we, in some sense, I often think of science as, putting down a jigsaw puzzle. And the easy parts of the jigsaw puzzle are at the very edges, which in some sense, are the very small and the very large, where life simplifies. But there's this huge kind of messy middle, this kind of limits of great complexity that I think science is now approaching. And indeed, if we take a point of view that we are discovering nature's Lego blocks, you could argue that we discovered in life genes and DNA and cells and molecules. In matter, we discovered particles and waves and atoms and molecules again. And in information, we discovered bits and codes and algorithms. And I would argue in all three fields, we're just on the edge of starting to engineer these realities ourselves. We have genetic editing in the life sciences, we have quantum technology in material science, in physics, and we have AI and deep learning in artificial intelligence in the information sciences. And again, I think it's interesting to see how long these timelines were to get to these kind of key technologies. So, for instance, DNA was discovered almost 70 years ago, Now it took 60 years to discover, decode, read, understand, and now rewrite this kind of book of DNA. And of course, now we live in a time of incredibly fast expanding genomic data, particularly I think in last years. And just to set the context, if you think of all the information, the digital information in the internet, it can roughly be encoded in 1 gram of DNA. So bioinformatics is going very fast. Digital information is roughly doubling every 2 years. Biological information doubles every 6 months. And I think the last 12 months, it must have been even more. As I said, we now have the tools of genetic editing, awarded the Nobel Prize in Chemistry last year. And biologists are embracing this world of engineered life. As it's often said, we are all the winners lucky winners in a cosmic lottery, because our particular DNA has been chosen to be expressed in a living form. But of course, the potential shapes of life are vastly, infinitely bigger. And biologists are trying out completely different things, different codes than the code and DNA is using, even completely different molecules. So I would say in physics, we are at a similar stage. Again, there's a long timeline. You could say it started in some sense with Feynman's famous lecture, There's Plenty of Room at the Bottom, where he said there's no principle in physics that do not speak against the possibility of maneuvering things atom by atom. And I think we're now getting into the stage where, in some sense, the technology of nature itself, that is quantum mechanics, is being used to build our own technology. So we are entering the age of macro or meso quantum devices in quantum commutation, in quantum sensors, in computers and materials. And so it's in some sense a vastly expansive view of what physics is. And in fact, in some sense, it's also the confluence of the technology of life, of biology, and the confluence and of the technology of matter itself. And so that's extremely exciting. So I would say the third wave that's kind of happening is this huge wave in computing and big data that's also driving science. So as you all know, we are living in an age of vast transformations in artificial intelligence. It used to be said, perhaps you know this famous paradox in computing called Moravec's paradox, which is that the easy problems for human beings, like playing soccer, are hard for computers or robots, while the hard problems for human beings, like multiplying large numbers, are easy for computers. And that's because, of course, the architecture of computers and humans is very different. Computers do not learn, they're not adaptive, they're not shaped by evolution. On the other hand, they have great advantages of having an open architecture, and they never complain. And now, of course, we're living in a time where, in some sense, we see a shift where computing is starting to be based essentially on kind of human thinking, and deep learning is now transforming our lives. There are many practical applications, but I would say that perhaps the most deep applications of this revolution in artificial intelligence can come in pure science. For instance, there was a very remarkable breakthrough last year when there was an annual competition among chemists where they are given the chemical structure of a couple of proteins, and then the game is to predict the shape of the protein. And there's a lot of knowledge, of course, within chemistry, but the AI program developed by DeepMind, Google's DeepMind, actually beat the competition in a pretty dramatic way. And so there is this new way of understanding pretty advanced, and I would say crucial elements in the structure of science. And I think we see many more. There's a lot of discussions among mathematicians that when deep learning will start to think and work with mathematical structures, whether it's prime numbers or geometries or whatever, that one thing that perhaps the landscape, the map of what's interesting math or less interesting math might dramatically shift. Clearly, we are extremely biased in our view of the unknown. And I would even say that all these breakthroughs are reinforcing themselves. We might have much more powerful, perhaps quantum computer-based artificial intelligence that will vastly increase our power to see structures in great complexity. So I think that as scientists, we should ask this question. Now, if we in some sense are able to understand with the aid of computers or just by ourselves collaboratively, much more involved and complicated structures, is there anything there to be found? Now, is there kind of simplicity hiding in this vast complexity? And I think we have to be honest that this is a completely open problem. Also, people in deep learning have essentially no idea which class of problems can be addressed in this way. Usually, any breakthrough is a great surprise to everybody involved. It's not clear how robust these results are. It's not clear whether they generalize. It's not even clear whether they can be understood in the way we think we can understand the basic laws of nature. But there was a wonderful series in the Wall Street Journal that's about career of the future, and I love this one. One of the examples was a robot psychologist, and this is not a robot that will do psychotherapy on you. We all need it, I guess, right now. But it was the other way around. Now, if you want to ask a robot how he or she is doing, you probably have to put the machine on the couch and interrogate it, just like you interrogate human beings. So one way to make these machines explain what they discover is, in some sense, have them answer questions about that and start a conversation. So with this, I now want to ask you, where and how can we expect to find new fundamental laws of nature? And I would say there are, to this answer, the question immediately would trigger two different points of view, depending on which field of physics you're active. So as a particle physicist, I think we are all skewed to think that, and I'm using this metaphor of garbage versus beauty. I learned that from David Gross. I think it's very, very addictive. So we see a lot of garbage out there. But then, we know we can find beauty if we reduce it to the elementary building blocks. And in fact, there's even a theoretical argument for this. If you just zoom in, a lot of details will become irrelevant and life simplifies. So I think there's this reductionist frame, which has been extremely successful in reducing a huge part of reality to something that easily fits on a t-shirt. And there is some kind of aesthetic feelings that go along with that. Perhaps, ultimate example is Paul Dirac, who famously said that it's more important for our equations to be beautiful than to have them fit experiment. And we can start to discuss what he exactly meant by that. But there is a totally opposite point of view, which I would say typical condensed matter physicists would have. So if they say, look at a glass of water, you can look at 10 to the 24 H2O molecules. That's a very complicated and inefficient way to describe water. And so we know there are beautiful laws of nature, say the laws of hydrodynamics, the laws of thermodynamics, that emerge in a limit. In fact, in a limit where essentially we take the number of particles to infinity. So again, it's a mirage. It's something that the full mathematical structure is never fully in reach, because it's an ideal situation. In the same way that I think we probably are looking for the ultimate reductionist point of view when we go to the smallest possible length scales. And something which I found quite an interesting observation made in this context was done by John Wheeler, who said that every law of physics pushed to the extreme will be found to be statistical and approximate, not mathematical, perfect and precise. And he made a very important point of view, that if your fundamental laws are approximate, you might say, well, they're not truly fundamental, but they have the wonderful ability then, to evolve and to be perhaps more flexible and to survive. And if you want to present a candidate for a law of physics that you truly feel will be able to sustain whatever will come in the future, then perhaps the second law of thermodynamics would be a very good candidate. So we just have to recognize that if you think about the building of science, if you think of it in terms of all its different components, that there are these kind of two arrows to go to larger and smaller scales of reduction and emergence. And they have to be kind of treated in a kind of an equal fashion. Now, I would claim this is not only true for science itself, it's also true for how science is being applied. So a few years ago, we published this little booklet, The Usefulness of Useless Knowledge, which is the title of an essay written by the first director of the Institute, Abraham Flexner. I love the title. And, it fits, I think, our image of progress that many of us have, where we start from theory, we move to experiments, and then finally to applications. So we have the completely uselessness of Einstein equation that turns out to understanding the curvature of space and time, the specific phenomena of gravity. And finally, we can implement this into our GPS systems. And that's why we find our ways. And, this is a kind of a very, I think, canonical way of thinking of how fundamental science can be useful. But again, here, there's a completely opposite one. And I'm tempted to write a book with the title, The Uselessness of Useful Knowledge, because there's an exactly opposite way you can go. So think again, of thermodynamics. It started with tinkering with steam engines, noticing that it's very difficult to improve them, then, do some complicated calorimetric or other experiments, and finally discovering this fundamental law. The second law of thermodynamics. And there are many areas, I would say, in science right now that are in this particular phase. I would, again, you could, if you look at computer science, now that started in the first framework with thinking about abstract machines at Turing, Gödel, Turing, von Neumann, and then to our computing machines. AI is actually completely the opposite. And often people complain that the current stage is more alchemy than science. But we should just have to recognize there's a long tradition of going from tinkering to fundamental truth. Now, we should also recognize that, for instance, even in physics, if we take these two poles of condensed matter and particle physics, that many of our fundamental laws and concepts have kind of emerged, I would say, in synchronous or very closely connected to each other. The spontaneous symmetry breaking was arguably first seen and understood by Anderson in the context of superconductivity. Of course, now we have it as one of our key elements in the Brout-Anglaire Higgs mechanism in the Standard Model. Gauge fields, emergent gauge fields, are quite important to understand many quantum effects like the quantum Hall. And of course, we know they're key to our description of fundamental forces. There's a rich context of topological defects in matter. And I would say that now we see an equal multiplication of defects in fundamental physics, whether it's monopoles or strings or branes or what have you. Condensed matter theorists were very soon to discover that materials can have boundaries, and the theory living on the boundary can be very different than the theory living in the bulk. And I would say that's now a key element in understanding quantum gravity through the context of holography. Even if you think about particles, of course we have our 17 particles of the Standard Model, but in fact, if you look into the range of quasi-particles, you see a huge zoo, an enormous diversity. Of course, started with holes and semiconductors, the phonons in sound waves, the magnons in spin waves, fractons, anyons. Probably the first discovery of Majorana fermions will be in these quantum bits, qubits. We have polaron plasmons. There is a tremendous zoo of quantized waves, I would say, in condensed matter physics, and it is exactly described by the same kind of mathematics. So if you ask, what is the most productive view on concepts in physics, as a little interlude, I want to share with you a really wonderful paper written by a famous mathematician, Bill Thurston. Unfortunately passed away. He was one of the great geometers. And he wrote a paper with the title On Proof and Progress in Mathematics. And in that paper, he raised the question, what is the best definition of an object? And he took a thing which is like bread and butter to a mathematician, which is the derivative of a function. So he asked, what is the right way to think about the derivative of a function? And then he starts, well, the first way is the formal definition that, if you take a formal course in analysis, you're tortured with the so-called epsilon delta definition. And quite interesting, he makes a mistake in the writing it down in the published paper. But he said, well, that's not the only way to look at it. You should also think of it as a rate, like as velocity. And if you think about it as a velocity, you immediately knows that the derivative can also have, can be a vector, can have multiple components. Or you can think of it as a slope, as a tangent. And that immediately tells you, you can also understand functions of more than one variable. Well, think about it as infinitesimal, what's the original view of Newton and Leibniz. Or think of it in a discrete way, as an approximation of a discrete way in which things are jumped. Or think of it symbolic. If you are able to differentiate functions of a real variable, then you can also differentiate functions of a very abstract algebraic function. Or think of it as the linear approximation. Think of it as zooming in, as a microscopic view on science. Or, and then he comes at some point at definition 37, I won't go through you, but his point was at some point, I needed definition 37 to make sense of what is a derivative. And I think actually we're in a very similar stage in terms of what we think of our fundamental laws. So I think the closest to a derivative to a modern theoretical physicist is a quantum field theory, a local quantum system. Trying to combine quantum ingredients, possible symmetries and representations, and a piece of space-time. And we know if we combine the two, we get this unique structure, quantum field theory, that pops up everywhere, whether it's condensed matter, whether it's cosmology, whether it's particle physics. Now, there are, I would say, equal number of views on what a quantum field theory is. I probably could list 37 too. Now, we can think of it in terms of the local operators of a field theory. We can think of it in terms of its scattering amplitudes, where we know deep mysteries are hidden. We can think of it in terms of spaces on a boundary. We can think of it in terms of putting it on different topologies. We can include defects. And all these views give, I would say, the concept of a quantum field theory start to enrich and enrich. What we have learned, as I said, from this beautiful field of topological insulators, there are systems where in 3 dimensions, you have a bulk material that's an insulator. But on the surface, it could be a conductor. And so it means that you have even a kind of a hybrid construction. In fact, you can even have interfaces between these 2-dimensional surfaces. So 1D structures that have an even more complicated physical structures hidden into it. We also know that in some sense, none of these points of view are ultimate. For instance, there are famous dualities. So if you think about a field theory described by some classical degrees of freedom, number of particles and forces, we know that once you turn on, say, h bar, you can have a continuous set of field theories, quantum field theories, that smoothly extrapolate from the one to the other. So even 2 sets of degrees of freedom are in some sense dual, or they are equivalent. It's like using 2 different languages to describe the same physical phenomena. There are 2 different classical limits of one quantum object. And this kind of landscape, or this space theory space, is incredibly rich. We know there are deeply embedded, strongly interacting quantum phenomena that can never be understood through the lens of a semi-classical intuition. In fact, there are even systems that have no degrees of freedom that can change, and so are completely isolated. So mapping out this landscape is extremely complicated and involved. There are some efforts to do this in a top-down manner. So you can start with the renormalization group. That's perhaps a bit technical. You can think of theory space and start with say, ultraviolet complete theories that can stand on their own as fully, at minimal distances, and think of the flow in that landscape, and somehow come to some perhaps finite set or limited set of large-scale infrared behavior. And so there's beautiful mathematical work in this. For instance, there's the famous tenfold way, the kind of symmetry groups that can possibly appear in the infrared in terms of quantum mechanical symmetry systems. So there is there are some kind of top-down approaches, but I would say it's still largely uncharted territory. Now, I think this view of having this emergence and reduction happening as two ways in which fundamental laws can appear, either in great complexity or going to very small distances, has been really put into kind of upside down with some recent developments in quantum gravity and string theory. So this will not be a seminar about string theory, but it has, I would say, triggered our minds that we should have a more inclusive view of what physics is. So one of the most exceptional breakthroughs that happened, I think, in the field of quantum gravity is that we discovered this kind of famous gauge-gravity duality, that a system of branes, that is a system of gauge fields on some dislocation on some space that might be of smaller dimension, can be equivalent to a gravitational theory in the bulk. That is to say, there are these famous ADS-CFT correspondence that basically tells us that there is an equivalence, really, between studying strongly coupled quantum systems with no mentioning of gravity at all, and a gravitational theory that actually is in one dimension higher. So I think this is absolutely fascinating, because I would say the most kind of disturbing part of this is that Einstein's theory, that I and many others would always have put in the category of a beautiful reductionist point of view, because it's clearly a fundamental underlying layer of reality, could actually be an emergent phenomena. So in quantum gravity, again, we have a large scale and a small scale point of view. Clearly, they are using completely different languages. We understand gravity in terms of the curvature of space and time, and we understand quantum mechanics, not in terms of geometry, but in terms of more of algebra, of probabilities, of superpositions, of entanglement, concepts that are extremely far removed from the language of geometry that Einstein so much loved. And I think what we are learning now is that, first of all, these two should be kind of equivalent. And perhaps the most fundamental point of view is that gravity is an emergent phenomena that appears if we study quantum systems of large degree of freedom. So in that sense, Einstein's equations can emerge out of the complexity of quantum theory, of quantum systems, in the same way as the second law of thermodynamics emerges out of the behavior of many particles. So that means, for instance, that the laws of Einstein's laws, particularly the laws of black hole mechanics, are not just analogs of the laws of thermodynamics, but are actually very similar. So there's a second law of black hole mechanics, where if you add two black holes together, the area of the horizon of the composite black hole will all be more than the sum of the two individual ones. There's a corresponding temperature, which is the Hawking temperature that you see here on the left. And this actually shows that there is at a very deep level an equivalence. And if you think of general relativity as one of your favorite theoretical constructs, then you have to allow in your mind that this might actually be an approximate statistical theory in the sense that John Wheeler spoke about. Now, building this dictionary is absolutely fascinating, because you can push it in many ways. And one of the most exciting thing I feel is that it's linking two fundamental discoveries that actually Einstein made, actually here in Princeton in 1935, which is on the one, oh, sorry, I should first say this, that of course that this is some sense most brought back, as I said, in the context of black holes. Black holes are, many people like to call them, they are the atoms of the 21st century, in the sense they have a big mysterious object that we know they're out there. If you look at the black hole from a gravitational point of view, it's the simple possible object that we know. It's literally just a hole in space. Whereas if you look at it from a quantum mechanical point of view, it's the most complex object that's out there. It's the most efficient storage device of quantum information. And the fact that these two concepts can be linked now in a theoretical framework has tremendous consequences. For one of the consequences is people studying quantum information are now actually very interested in black holes and the laws of gravity. And the Bacon-Hawking formula of geometric entropy connects these two concepts. The thing I was alluding to is that the two discoveries of Einstein are the two discoveries he made with his collaborators in 1935. The first is the famous Einstein-Rosen bridge, the fact that you can have what we now call wormholes, that general relativity allows for non-local interactions, 2 points in space-time that can be connected by this kind of a tube. And the second is, of course, the famous Einstein-Podolsky-Rosen paradox, the fact that you can have entanglement, that you can have non-local phenomena in quantum theory, in quantum physics. And the present point of view basically tells us that these are two sides of the same coin. In the gravitational incarnation of entanglement is actually the fact that we have these kind of more complicated concepts of locality. Now, I want to end by perhaps a final philosophical point of view. So this is a famous drawing from John Wheeler. It's in this big Bible, Gravitation. Some of you might know it. And I remember seeing it even as a high school student, and I was like totally flabbergasted by it. So Wheeler had this view, he called it from bit, that in some sense, the ultimate layer among reality is information. And the question is, I would now say quantum information. And reality is made by linking these constituents, linking these elementary pieces of information. So I love the kind of this knitting the sweater of reality. But I would actually say that in the context of my lecture today, I would say my column is that perhaps this is the way we should look at physics too. No, we have our building blocks, whether they're atoms or particles, waves, quantum qubits, and what we can do is we can connect them together. Nature does this by building the phenomena that we see around us, but there's nothing that limits us in building reality, enhancing reality, and creating, so to say, a much bigger sweater to study. In fact, as I said, I would like to argue that physics is about all possible arrangements of matter and energy. And now there's only a limited range of configurations that we know has been explored in the universe. And I think, we are on planet Earth are adding to that. Clearly, we do this in our particle colliders by creating phenomena that are actually haven't studied before. But there's a vastly larger universe of arrangements of matter and energy to be discovered. And the big question is, in that vast space, are there new fundamental laws that we somehow can map into our mathematics, which of course is a much larger space, because reality is only a small part of mathematics. In fact, to put things very sharply, we could even perhaps turn things around. Now, can you reverse engineer a law of nature? Or which laws of nature can reverse engineer? Can we think of certain phenomena and then you create a complex matter system, quantum matter system probably, that actually describes these phenomena. And actually we're moving in that direction. Just to give a little example, people are engineering tensor networks or quantum information tensor networks that are in some sense engineering the spaces that people in quantum gravity are studying. So you can build your little ADS space, anti-de Sitter space, in the lab and study it, and do kind of experiments that probe fundamental laws. So I think that's extremely exciting, and I would say that's part of our future. Now, coming back to the role of understanding all of this, I would say that we are a little bit in the same situation as mathematicians trying to understand the derivative of a function. If we want to understand physics, we have all these overlapping theoretical paradigms, right? So I just put some of my own favorites here. And we have to conclude that all these concepts are very rich. They cover certain parts of physics. Sometimes we see that there is a phenomena that's covered by more than one paradigm, and we can have beautiful translations, there are dualities, etc. But it's clearly not the case that we have a grand unified view of all physical phenomena. And perhaps we'll never get this. Now, there's I think, a very deep question that philosophers ask, an epistemological question. How, in the end, will we understand the world? If we think of the world, the universe of all phenomena, what would we build? Will we have the equivalent of a globe, that is a global understanding, or will we build more like an atlas? Or do we have maps that cover certain parts of physical reality? And then, just as in an atlas that you might still have as for sentimental values in your bookcase, then there are usually instructions to tell you how you go from page 12 to page 13. And so we need these kind of instructions to go along with it. So I think that's an open question. And I think it's probably extremely optimistic to expect any kind of global point of view. And perhaps we should embrace this kind of more patches of understanding and their interconnectedness. Anyhow, I want to conclude that what I feel, and this is my shot of optimism to all of us in these dark times, is that if you look at the progress of physics and see scientists as modern explorers, I would say that we have been traveling through a beautiful river, which is studying what is, and we're now entering this grand ocean of what could be, and it's our task to I would say not get lost, be adventurous. I would say be not too afraid of the many sea monsters that in our imagination. And I would like to say to all of you, bon voyage.